In this video, we solve problem 103 from section 5.5 of the Larson Calculus text, 10th edition. We're told that a number of medical procedures of a certain type in the US for the years 2004 through 2010 are shown in the table, with x equals 4 corresponding to the year 2004. So x equals 5 is 2005, x equals 6 is 2006, x equals 10 is 2010, and so on. So for the years 2004 through 2010, there were 603 of these procedures done in 2004, 542 of these procedures done in 2005, 466 of them done in 2006, and so on. In order to enter that table onto Desmos.com, I just clicked enter here from this cell, and that brought up a new cell. Then I choose the add item sign, and then choose table here, and then you can just type in your data. So I started with 4, and then I go 5, and then it automatically populates all the way up through 10. And then I just typed the corresponding y values from the table in the textbook. In order to get that data set, if you select that little open circle next to the y values, it plots the points. Now, in order to get the correct window for our graph here, I looked at the y values in our chart and I said, okay, the lowest y value in the chart is this 350, the highest is 600. So I want to make sure that my range of y values includes all of the y values between 350 and 600. That's not the range of the function, but you know what I mean. The range of y values in the viewing window. And then I knew that my x values had to be between 4 and 10. So I said, let's go from x equals -1 or -2 or something like that to 10 or 12 and plot the points. So if you want to do that, you can always go to this little wrench here and you can change the bounds for x and the bounds for y. That's what I did to create this graph. And if you want to zoom in a little bit, you can just click the plus sign there. Oops, I'm zoomed in too much. I want to see my axes. So that's what we have if we make it possible to see the axes. Now we're asked to use the regression capabilities of a graphing utility to find a linear model, a logarithmic model, an exponential model. And I initially called it a polynomial model, but it's more like a power model. It's a constant times x to a power. But if that power was a natural number or possibly 0, then it would be a polynomial model. But I'm just going to call it a power model because that power might be, 1/2 or 0.5, or it might be a pi or something like that. It might be a number other than a natural number or 0. In that case, it wouldn't be a polynomial. It would be just sort of a power function, like x to the 1/2 is x with a rational exponent, and the graph would be a root. So we're going to find a linear model, a logarithmic model, an exponential model, and a power model for the data. And we're going to look at the r-squared values for each of those. And we want r-squared to be as close as possible to 1. And the one that's closest to 1 is what we're going to call our best model. And we're also going to graph those models for the various types and see just how the data fit through those particular functions. So for our linear model, basically I want a y equals mx plus b. Y is the number of procedures and x is the year. So if I just associate y1 with mx plus b, m and b are determined. Our slope is -40. The y-intercept is 743.25. They might say, well, what does that 743.25 mean? Well, it just means that approximately 743 of those procedures happened in the year 2000, provided that this trend actually continues outside of the years 2004 through 2010. So assuming that the data looks similar to this and that a linear model is appropriate, then that y-intercept would tell us that about 743 of these procedures happened in the year 2000. And that slope of -40 just tells us that the number of procedures of this type is decreasing at 40 procedures per year. So every year there are about 40 procedures less that happen as compared to the year before. That's what we get with our linear model. I want you to notice that the r squared is at 0.9561. So it's not as close as I would like to 1, but it's fine. It's within 5% of 1. So it's pretty good. So that's our linear model. As far as our logarithmic model is concerned, this is where we would say, okay, I want a natural log function, but I want to multiply that natural log by a constant. So that's going to stretch it vertically or shrink it vertically. And then I want to add a constant to that logarithmic function. So that's going to move the graph up or down. And it's what this Desmos is doing is it's finding the values of a sub 2 and b sub 2 so that this model fits the data. And again, it's choosing a sub 2 and b sub 2 to minimize the sum of the squared errors. That's the difference between the y values in our data and the y values that are given by this function. So that is what our logarithmic model looks like. Here, the r squared is 0.968. I noticed that we've got a lowercase r squared here and a capital R squared here. I don't really know what the difference between those two is. But from what I've seen online, this capital R squared is supposed to be related to the amount of variance in y that is due to the variance in x. But I'm not sure, these sources that I'm reading, I'm not sure if they're trustworthy sources. I mean, they seem relatively trustworthy to me, which is why I'm repeating it to all of you, but I might be wrong. I will say that the r squared is close to 1 at 0.968. And as I look at that, the fit between that logarithmic model and the data and the fit between the linear model and the data, it looks like the logarithmic model is better. And the a and b value that we need are b equals -265 approximately. So we take that natural log function and we multiply it by a negative. So that's going to flip it upside down and then stretch it vertically by a factor of 265. And then we're adding 967 to all the y values. And that's what gets us this graph. So that's our logarithmic model. As for the exponential model, we're going to say, I want y to be a constant, or y to be sort of the form a to the x, essentially. But we want to multiply by an extra constant if necessary. And I would typically add a constant that would move the graph up or down. But the form of the model in the text was a constant times a constant to the x. And I think they used a times b to the x. I used a sub 3 and b sub 3 because it's the third model. Because I was using a sub 2 and b sub 2 for the second model, and so on. So I'm using the subscripts to sort of help me keep track of which model those particular values, those parameters go with. So I want to choose a and b to minimize the sum of the squared errors between the y values predicted by the model and the y values in the data set here. That's what the graph looks like. Our r squared is 0.965. So it's not as good as the last model, but it's close. The a value that we need here, that extra factor that stretches it vertically, is 840. And the base of our exponential function is 0.916. So since it's a fraction between 0 and 1, that function decreases as you go from left to right. And you're raising that to the x power, where x is the number of years since the year 2000. And then this is the one that I called a polynomial model at first. It's like a constant times x to a constant power. But it's not necessarily a polynomial because that constant might not be a natural number or 0. It might be some fraction. It's most likely to be some fraction. So we'll just call this a power function model. We're trying to find the a and b that make this model fit that data. Looks like that. Actually looks a lot like the logarithmic model. And then the r squared is 0.9617. Which is still good, but it's not as close to 1 as model number 2. So model number 2 has the r squared that's closest to 1. And I think my understanding is that means that's the best one. I don't really know for sure. It's been a while since I've had statistics, and as I look that information up online, I really don't know what that means. I read somewhere that's called coefficient of determination, so I might search tomorrow and try to figure out more the details about that. But one of the online sources that I read said that it was a proportion of variance in the dependent variable that can be explained by the variance in the independent variable. And this is the link to the source where I found that information. And the second model is best because the R squared is closest to 1 for the second model. Now for each of those models, all 4 of those models, we want to compute the derivative, evaluate the derivative, and then evaluate the derivatives at the x value corresponding to 2008. And then we want to interpret the derivative in each case. Well, with the first model, it's just a line, right? We say, okay, well, what is the derivative? It's the slope of the line. So if you evaluate f, or the f for that first model, and you take its derivative, well, you just get the slope, which is that negative 40. Again, y was the number of procedures per year. And I guess we shouldn't write y equals. Y was the number of procedures per year in that original model, and then x was the number of years. So this is just telling us that the number of procedures of that particular type was decreasing by 40 units, by 40 procedures every year. So I guess this procedure was becoming less and less popular. If we want to, we can plot that point. And that's a point using the model, not the actual data. And the derivative, actually, if I wanted to graph it, I could type y equals. It looks like that. It's just a line, a horizontal line, because we were talking about y equals mx plus b. So the slope of that line is, or the derivative of that function is just the constant, just the slope. Okay, so that's our first model. For the logarithmic model, this is what it looks like. I'm going to stop graphing that first model now. This was supposed to be the best one. If we take the derivative of this, derivative of a is 0. The derivative of a constant times natural log of x is that constant divided by x. So we get that. And if we want to, we can graph that function. Notice that when I ask Desmos to graph that second model prime, it gives me the same function that I get when I calculated that derivative by hand. So we know we did our job correctly. And we will evaluate that derivative at x equals 8. And that gives us that negative 33.18. So that's saying in 2008, the number of procedures of this type was decreasing at a rate of approximately 33 procedures per year. So in the year 2008, the number of procedures was going down by 33 per year. And we can plot that point on the graph. We can find the slope on the graph of the derivative function. If we wanted, we could draw the tangent line, but we won't this time. So really all we're doing is finding appropriate models, saying which one do we like best or which one do we think fits the data best. And then after that, we are differentiating using our basic rules and then interpreting that derivative value at a particular x value in terms of the real world interpretation of the y or the variable y and the variable x. So for our exponential model, we've got a constant times a constant to the x. Those constants are denoted by a sub 3 and b sub 3. If we want to know what they are, we can just type a sub 3 and b sub 3. These were numbers that were found by Desmos when it fit that model to the data, minimizing the sum of the squared errors. That's how it's choosing that a sub 3 and b sub 3. Now, when we differentiate this, we're going to differentiate using the a to the x rule. So a sub 3 is just a constant, so you write that down. And then I've got a constant raised to the x. The derivative of a constant raised to the x is natural log of the constant times the constant raised to the x. So you get the same exponential every time, you just have to multiply by the natural log of the base. So the derivative actually looks like that. And if we ask Desmos to compute f prime, notice that their f prime and our f prime are the same. So we know our calculation is correct. If we evaluate our f prime at x equals 8, we get negative 36, negative 36.5. So it says, okay, if I'm using this model, the number of procedures of this type was decreasing at a rate of approximately 37 procedures per year in 2008. So that's what that f prime means, according to that particular model for the number of procedures per year, or the number of procedures in year X, where X is the number of years since the year 2000. And of course, we could plot the points on the graph and on the derivative graph. And again, this orange value is not actually associated with the data. It is or this orange point, it is a point on the graph of the model itself. So this is the Y value that's given by the graph. The actual data in the year 2008 might give you a different number of procedures. Well, actually, we know it's going to give us a number of procedures. It's a whole number because you don't have like part of a procedure. You either get the procedure done or you don't get the procedure done. But our model gives us some decimal approximations sometimes. So this says in 2008, there were 417.8 of these procedures done according to the model, or approximately 418 of those procedures. And the number of procedures of this type was decreasing at that moment in the year 2008 by about 37 procedures per year. And then for the next one, we want to find a power function. So we're looking for a constant times x to some power. The constant in front and the power itself are to be determined by us, or actually really to be determined by Desmos, minimizing the sum of the squared errors, the difference between the predicted y values from the model and the y values from our data set. And that's what the curve looks like. Now, when we differentiate, we're just going to use the power rule. So you have your constant, write that down, and then you bring your power down, and you multiply by x to the 1 less power. And so that's what the derivative looks like. And then if I evaluate that derivative at 8, I get negative 28.6. So we're saying in 2008, the number of procedures of this type was decreasing at a rate of approximately 29 procedures per year, according to this particular model. And you can plot a point on the original graph, and you can plot a point on the derivative graph. And we see that in 2008, according to this model, there were 414 of these procedures done. And that according to this model, that number of procedures of this type that was done was decreasing at a rate of 28.6 procedures per year. And so that's that. That's how we use the regression capabilities of Desmos to come up with models of various types. And it's really nice. It's finding those coefficients or those constants for us, those parameters in our model. And then we can differentiate the functions and plug in particular values, and that will allow us to practice interpreting derivatives in real-world applications, and also practice computing the derivatives by hand and confirming that our derivative is correct by comparing the graph of our computed derivative with the graph of f prime as generated by Desmos. So that's it for exercise 103 from section 1.5. I think we're pretty much done with the curve fitting now. The next video, we'll look at some other applications. I think this next one is about inverse functions and exponential models.